Dear students, so welcome to the next lecture of digital communication. So in the last lecture we were discussing about the error correcting codes and error detecting codes. So we will continue our discussion, and in today's lecture I will introduce you with the concept of general linear block codes. So in the last lecture, towards the end of the last lecture, I stopped here at this example of designing a Hamming code. Okay, so these Hamming codes, these are the general family of block codes with this N and K. Okay, so N is the size of the final code word and K is your message length. So they are all defined by this NK, and we saw in the last class how we can design the check bits and how we can generate the the code words, and then when we receive how to decode if there is an error and how to find out which bit was in error. Okay, so today we will try to revisit the same concept of Hamming codes, but from a more generalized and systematic point of view. So imagine that we have k bits of message. Okay, and then you are doing some form of mapping, okay, to generate a n bit code word, right? So this mapping, okay, whatever it is, if we can generalize this function that would take any input which is k bits and generate a n bit code word out of that, then that would be great, right? So that's what we are trying to do, and see how that could be done. So in the previous class, in the example that we were doing, especially this example that we were doing, we were basically following some rule to find out the k, I mean the n bit code word, right? um, we were trying to follow some rules. For example, we would generate the check bits according to some rules. So for example, the first check bit will be at the 2 to the power 0th position, the next check bit will be at the 2 to the power 1th position, and so on. And from there you could generate the 4 check bits, and then you can have a 12 bit code word, right, out of a 8 bit message. Okay, so basically you are mapping these 8 bits to generate these 12 bits, right? And this mapping rule was given by all these methodologies. So you are having C1, C2, C4, C8, and then you are having the entire code word like this, where you have the different message bits, and then in between the message bit you have the check bits embedded according to this rule. So now if we can generalize this process and have this k bits, which is input to a channel encoder, and we have n bits, then how to mathematically represent this channel encoder so that any mapping of this input k bits which generate a particular unique n bit code word for this k bit messages. So that's what we are trying to achieve here, and this representation is equivalent to the previous representation what we were doing, but this one you will see is more convenient and more easy to theoretically represent and generalize. So let's imagine that you have a message word u which is defined by this. So you have, these are the individual bits of the message. So you have k bit messages 1 to k. This is a row vector of length k bits, okay, and this is encoded by the channel encoder to produce a code word C which has this n bits, okay, so C1, C2 up to Cn, which is again a row vector of length n, and usually n is greater than k. So the code rate of the code is defined by k over n and is equal to the number of message bits per coded bit. An efficient code will have a code rate close to unity, okay, and the channel encoder introduces redundancy into the channel input stream. So these things we all know, okay. We know what is code rate and what is redundancy, but the way of looking into this encoder is different here. So let's move on and let's define a matrix G such that when you are multiplying your input message with this matrix G, then you obtain the code word C. So in other words, in a nk linear block code, the encoder operates according to this equation, okay. So where G is a k cross n matrix called the generator matrix. So this k cross n is important. So this U, this is a k, or rather 1 cross k, okay. So this is a k length k vector, length k row vector, this U, okay, and the C is basically a length n row vector, okay. So basically C is 1 cross n. So this G has to be k cross n, so that when you multiply this 1 cross k with a matrix G which is k cross n, then the output that you get is C which is 1 cross n, okay. So this matrix G, which is also called generator matrix, has to be k cross n, so that this multiplication, this matrix multiplication is compatible. So if you write the generator matrix like this, where G1, G2, etc. up to Gk are the rows of the matrix capital G, then you may write C, which is equal to U times G, is basically Ui. So each bit in U multiplied with each row in the generator matrix, and then you sum this over I equal to 1 to k. So this is what is the general theory of linear block codes, or this is a means to generalize the generation of linear block codes from the message bits, okay. So now let's look into different other aspects. So for example, by definition, a code is said to be linear if if the entry-wise modulo to sum of any two code words yields another code word. Okay. So the claim that we are trying to make is that the code defined by equation 1 is linear. So we are claiming that this is linear. Okay. So let's try to prove that. So consider any two code words C1 and C2. Okay, corresponding to two different message words U1 and U2. Then according to the rule, the encoding rule, you have C1 equal to U1 times G, the generator matrix, and similarly you have C2 equals to U2 times G. So C1 plus C2, or the modulo 2 addition, so this plus, remember this is a modulo 2 addition. So C1 modulo 2 addition C2 will give you U1G plus U2G, and then you can write this in this form. Okay. So now if you argue carefully, you can find out that U1 plus U2, where this plus again is a modulo 2 addition, is another message word. Okay. So let me give you an example of this. So why U1 plus U2 is another message word. Okay. So let's try to focus on this part of the proof. Okay. So U1 plus U2 is another message word, and therefore C1 plus C2 is another code word. So this is fine, but you might ask why U1 plus U2 is another message word. So let's imagine that that you have a K which is equal to 3. Okay. So every message is a 3-bit long. Okay. So for this you will have 2 to the power k minus 1 combination. So that will be 7 combinations. So if you write them, any combination of 3 bits will only be these. Okay. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay. So let's take an example. Let's say your U1. So U1 is this one. Okay. And let's say your U2 is this one. Okay. So just randomly select your U1 as this and your U2 as this. Okay. Without loss of generality. So if you just do the modulo 2 sum of U1 plus U2, then these two will give you what? 101 and 001. So this is just a regular binary addition. This will give you 1 plus 1 0. So this will give you 0 0 1. So 1 0 0. Okay. And 1 0 0 is another code word. Okay. This one. So 1 0 1 0 0 1 will give you, if you do entry wise modulo 2, this, and 1 0 0 is another code one. And if you do this for any two chosen code words, you will find that the sum U1 plus U2 is also part of this code. So that's why it is said here that U1 plus U2 is another message word, which is true. We have demonstrated it just now. You can check for any two chosen message word. You will see U1 plus U2 is another message word, and therefore C1 plus C2 is another code word. So therefore the code is linear. Now if the message bits appear in the code word unchanged, then the encoder is called a systematic encoder. Okay. So in the example of the previous class, let me go back a few slides back. So in this example, your code word was this. Okay. and the message words were only this thing, this one, this one, this one, this. So you can see inside the code word you have this check bits that are appended in between the message word. Okay, so basically if you want, you can also have a design like this where the message words appear first. Okay, so from D8 to D1, whatever they are, let's say 0, 0, 1, 1, then this 1, then this 0, then this 0, and then this one. Okay, so the message word appears first and then the check bits, whatever they are, appears next. So if this type of code is generated, then that type of code is called systematic code. Okay, and the encoder is called a systematic encoder. So since we are having a matrix G and you are generating your code by multiplying your message with this matrix, you can design this matrix in a way that in your code word you have the message words first, okay, then followed by your check bits. Okay, so let's say this will be the message or the entire U followed by the check bits. Okay, or you can also have the check bits first, let's say, and then followed by your message. Okay, so this both forms where your message bits appear in the code word unchanged. Okay, whether the message bits come first and then the check bits, or the check bits come first and then the message bits, in both cases, this one and this one, your message bits appear unchanged in the code word. Okay, so if you want this type of arrangement, you can define the matrix G, the generator matrix G, in such a way that you can have this, either this or this. Okay, so you may write your generator matrix, let's say, in this form where your IK denotes a K cross K identity matrix. Okay, and your P is a K cross N minus K matrix. Okay, so if that is the case, okay, then if you generate C, which is U times G, then this multiplication will give you UP and U. Okay, so this is basically the way of writing the generator matrix. Okay, so this line in between doesn't actually exist. This is just to show that this part of the matrix is a identity matrix and this part is a general matrix. Okay, I will show you some examples. So to identify this fact, in fact, let's take an example right now. Let's imagine that your K is 4. Okay, so in that case your G might look like this. Okay, so let's have this line, which is this line, and this part is easy to write. So this will be a identity matrix K cross K. So 4 cross 4 identity matrix would look like this. So the diagonal elements will be ones. Okay, and this part will be a regular matrix of ones and zeros. So it can be anything. Let me just randomly write this part. So let's say your n is 8, okay, and k is 4. So n minus k, so k cross n minus k, this part. So this will be, let's say, a random whatever. Let's say, so this entire G matrix would look like this, where this part of the G is an identity matrix Ik, which is k cross k, and this part is a regular matrix of ones and zeros. So your G matrix will basically consist of only ones and zeros, because it's a binary matrix, and then you are multiplying your message vector with this matrix, and then you are operating on this matrix um, in a similar way as you do matrix multiplication, but the only difference is that the addition here will be modulo 2 addition. So in that way you can generate the code word which is also consisting of ones and zeros. So now if you have this form of matrix G in this form of P and Ik, then if you multiply your message bits, then you will have this UP part comes first and then comes the U part, okay, because U times Ik is U, since this is an identity matrix. So this shows that the message bits appeared at the end of the code word, okay. So this example that we just discussed, here you have the check bits first and then the message bits. You can also write this matrix as I n minus k times p, okay. So you can generate a generator matrix also of this form, where you have an identity matrix that comes first and then the P matrix, okay. And then if you have your generator matrix like this, then in your code word you will have U first and then UP, okay. So in that case this form will be there. So your message will come first and then the check bits, okay. So basically this P matrix, when you are multiplying this P matrix with your U, this P matrix is contributing to the check bits, okay, here also, okay. So this is called systematic encoder or systematic linear block code, okay. And if you, so just remember one form, just remember this form, but both are valid, okay. In my lectures I will use the form that is printed here, but you will find in some other textbooks or other material you can find on the internet, you might find this approach also. Oh, by the way, this will be P transpose, okay. This is I n minus k and this is P transpose, okay. So so just focus on this representation for now, but this is also valid, and you can look up yourself for this other form of representation, and it will be nice that if you appreciate both forms, because they are just the same, okay, they are not different. So don't get confused, just try to appreciate the concept here. So if your generator matrix is in this form, then or in this form, then your message bits keep intact. Either you will have the message bits that comes at the end of the code word, or the message bit will come at the beginning of the code word. And this form of representation is called systematic representation. So for the systematic encoder given by equation 2, we may define the parity check matrix H according to this. So you can see, if your G is like this, then your parity check matrix is like this. You can have your G also as this, as I just said. So in that case, your parity check matrix will be like this. Okay. So these two are complement of each other. Okay. So if your G is like this, then your parity check matrix is like this, and if you do this G times H transpose, then you get 0. Okay. So where 0, this bold 0 denotes a k cross n minus k matrix of all zeros. Okay. So that's why this G and H are complementary. Okay. So if your G is of this form, then H is of this form. If your G is of this form, then H is of this form. And then suppose C is a code word, and therefore C equals to U times G for some message U. Then if you do C times H transpose, then GH transpose is 0, so you will have 0. Okay. So therefore, if your C is a valid code word, then you must have C multiplied by H transpose equal to 0. It should satisfy this condition for any code word C. So the code consists of exactly those vectors C which satisfies this. Okay. And if it is not equal to 0, then this is not a valid code word. And while you are transmitting this C through the channel, okay, and your received vector is not equal to C because of some error, then one way of looking into this will be that R times H transpose will be not equal to 0. So in that case, you can immediately say that there is an error. Okay. And if there is no error, then R will be equal to C, and then this will give you equal to 0. So that's another way of checking whether there is an error or not. So now we will go into another type of Hamming codes, which is called low density parity check codes. But before I go through this LDPC discussion, I want to show you a nice video. So I will stop here, and the video will come, which will give you a very nice overview of LDPC codes, and then I will come back to the main slides with the remainder of the discussions.
Often we need to transmit sensitive data, such as banking information, where every symbol in the message is vital. One mistake can corrupt the entire message. And no matter how we communicate, we face this problem. One kind of corruption occurs when a bit flips. The transmitter sends a 1, but it's received as a 0, or a 0 which is received as a 1. These are called errors. Another kind of corruption is an erasure, which occurs when the bits are so distorted that they're considered unknowns or blanks in the message. For this video, we will discuss this problem in terms of erasures because it simplifies the main ideas. While some communication channels suffer from less corruption than others, it's important to note that corruptions are bound to occur. No channels are truly noiseless. So the problem communication engineers will always face is how can we transmit our messages perfectly when we know some symbols will be lost in transmission? Realize we all face this problem during ordinary voice communication, when a word is misheard in a conversation. To recover from this corruption, we simply repeat ourselves. Technically, this is called a repetition code. It's the simplest error correction code. For example, if we have a binary message, it would be encoded before transmission into 2 copies of itself. This might be received, for example, with some erasures as follows. These erasures can easily be decoded by comparing the 2 copies bit by bit. Thus, the message would be decoded correctly. This compare operation is simple and thus can easily keep up with the speed of communication. Unfortunately, simple repetition fails whenever the same bit is erased in both copies. And because this is quite common, this strategy leaves us very vulnerable to failure. Also, it doubles the message length no matter the number of erasures. We express this efficiency issue in terms of code rate, where code rate is the original number of message bits divided by the total number of transmitted bits. Thus, the code rate in this repetition scheme is 50%. That means half of the bits are needed to describe our original message, and the other half are there to protect the message. If we use triple repetition, the code rate would drop to 1/3. As the rate drops, the protection increases, but there are fewer message bits sent. So a lower code rate is a more expensive design, since every bit we transmit has some cost. So there is a balance to strike between the code rate and the probability of failure. We need a coding strategy with just enough protection bits to prevent failure for any channel, whether we expect a high or low erasure rate, while also maintaining fast encode and decode operations. To solve this problem, we need to be smarter about how we use the protection bits. First, realize that with repetition codes, each bit is only protecting one bit of information. Instead, we could define a single protection bit that protects the entire message from a single erasure, no matter where it occurs. To do this, we use an encoder which counts the number of ones in the message, and then chooses a protection bit value to ensure that the total number of ones in the message is even. Used this way, we call this protection bit a parity bit. The sender includes this parity bit at the end of the message. Now, consider what happens when a single erasure occurs during transmission. The receiving decoder can correct this erasure with a simple operation. It counts the number of ones in the received message, and so it knows the erased bit must have been a 1. Notice that a single parity check bit yields quite an improvement to the code rate compared to repetition coding. However, the chance of failure has increased compared to repetition. With a single parity check bit, we can only correct a single erasure, and if 2 or more erasures occur, the code fails because there isn't enough information to reconstruct the bits. To decrease the chances of failure, we can divide up the message into distinct sets and include multiple parity check bits, where now each parity check bit protects a different set of bits from a single erasure. We call each of these sets a parity check set. And as we add more parity check bits, we increase the number of erasures we can potentially correct, at the cost of gradually decreasing the code rate. In general, the number of parity check bits should be at least equal to the number of erasures if we want to have a chance of correcting them all. However, we face the same problem with this approach. The code fails if 2 or more erasures occur in any parity check set. In that case, the bits can't be recovered. In 1950, Richard Hamming was looking at simple ways of correcting multiple errors when transmitting a sequence of bits. His trick was to use overlapping parity check sets, which made it possible to correct any 2 erasures. As a simple example, consider a 4-bit message and 3 parity check bits. Each parity check bit covers 3 message bits. Now, no matter where 2 erasures occur, the code will always be able to correct. In this case, we can't recover the first erasure right away, since both black and blue sets contain 2 erasures. However, the second erasure can be recovered first, because the red set has 1 erasure. And this provides the information we need to recover the first bit. This cascade effect, where one correction allows us to solve another, is a very important insight, because instead of correcting all erasures in one step, we can remove erasures in multiple passes or iterations. It's important to note that this kind of cascade effect only works if we have at least one set with only 1 erasure at each step, otherwise it would fail. This led to a decade of excellent research by many people who built on this idea of overlapping parity check sets. Much of this work was aimed at finding the right structure for the parity check set arrangement. But when we extended this overlapping approach to very long messages with many thousands of bits, we ran into a problem. This was because with longer messages, most assumed that we could use larger overlapping subsets. But having many large overlapping subsets turns the process of decoding the parity check bits from a simple operation into a complex puzzle. This is because when the subsets are very large, the chance of getting a subset in which there is only one erasure is very small, and this prevents that cascade effect from starting or continuing. Instead, the parity check bits must be solved using a more complex decoding operation, because now you are faced with solving a system of equations, which becomes more and more complex as the number of equations grows. But these more complex decoding operations slow down the communication process to the point where it's no longer practical to use. What we need is a code with very fast decode operations. So we are left with a final problem. How can we extend this overlapping subset approach to work quickly over very long messages in a way that can handle any erasure rate we encounter while maintaining a good code rate? In 1960, a doctoral thesis by Robert Gallagher discovered a new approach to the communication coding problem, which is in wide use today, particularly in cellular networks and data storage applications. Gallagher combined two key insights. The first was to use smaller parity check sets instead of larger ones. This improves the chances that many parity check sets will contain only a single erasure and enables the cascade effect to happen. This was key to keeping the decoding speed fast over long messages. Because it's faster for a computer to solve many simple problems instead of a single complex problem, which solves all of them at once. Gallagher realized that we need an amount of overlap that is large enough to protect each bit well, but not so large that the correction problem becomes very complex. He measures the amount of overlap by something he calls the density, that is, how densely the message bits are connected to the parity check bits. With larger subsets, we have a high density, that is, each message bit is connected to many parity check bits. With smaller subsets, we have a lower density, that is, each message bit is connected to fewer parity check bits. And this is where the name low-density parity check codes comes from. But aside from the size of the sets, there is also the problem of how to structure the connection between parity and message bits. And that leads to his second insight, which was inspired by the work of Peter Elias, who had recently shown that looking for the right structure for large subsets was relatively unimportant. Instead, he used a random subset arrangement. This simplified the problem compared to trying to design an ideal structure for the subsets, and remarkably, it did very well. And that's the key idea behind low-density parity check codes. Use small, overlapping, randomly assigned parity check sets. This allows us to solve erasures in a rapid cascade of simple operations, no matter how long the message is or what the erasure rate is, while maintaining a fast decoding speed. But there is one last insight to understand when it came to the actual construction of these codes. Recall that Hamming's construction focused on protecting each message bit with multiple parity check bits in order to better protect those bits in case of multiple erasures. The problem is this doesn't provide the same protection to the parity bits, which can also be lost during transmission. Notice that each parity check bit is itself only connected to one parity check set. Since any bit that is connected to only one parity check set is vulnerable, this leaves all parity check bits vulnerable. This can make correction impossible in some cases. For example, this would happen when one message bit is erased and two parity bits it's connected to are also erased. In this case, we are stuck because the cascade can't happen. And over very long messages, with many small parity check sets, this kind of failure would become more and more likely to happen. The solution to this dilemma is to instead view things in a more general way and protect the parity bits and the message bits equally. That is, we make sure all bits, message and parity, are contained in multiple check sets. And now we have everything we need to understand the basics of low-density parity check codes, or Ldpc codes. To see this in action, let's do a very simple example. Now let's say our message is 101. Recall that we chose our subsets randomly to generate the code. Encoding is now done by finding a collection of parity check bits so that all the check sets have an even number of ones. This involves solving a simple set of linear equations. Now imagine our message is received with 3 erasures as follows. To decode this message, we begin with the check sets that have a single erasure first, such as this one, and we repeat this process for every check bit until there are no more erasures left. That's one way the iterative process can work using low-density parity check codes. It's simple, fast, reliable, and can be extended to messages of any length. Today, many communication devices use Ldpc codes, and versions of Ldpc codes are being proposed for 5th generation wireless systems, known as 5G. But it's important to note that when these codes came out, they did not have a big impact at first, and were almost forgotten for many years.
I invented Ldpc about 60 years ago. There were no cell phones then. Data transmission was painfully slow, expensive, and error-prone. MIT's main computer had a computational power halfway between a modern cell phone and a coffee machine. Error correction coding was a fascinating theoretical problem then, studied by many mathematicians and engineers. Simple schemes were ineffective, but complex schemes were too expensive for 1960 technology. Ldpc was an interesting midpoint, cute and interesting to theoreticians, but 35 years before technological feasibility. That's the way research is and the way it should be. Hard research problems take years to solve and should not be overly dependent on details of current technological capabilities. Technological capabilities and research projects both proceed at their own pace, and applications result when both are ready. Thank you.
So welcome back after that very nice and interesting video. So as you saw in the video, so this low density parity check codes, the name low density means that there are less number of ones in this type of codes. Okay, so they are very efficient codes. They almost approach Shannon's limit, and by Shannon's limit I mean the Shannon's capacity limit. So this relates to another thing which you have already studied. So you know that the Shannon capacity is defined by this formula, and with coding, with this type of coding, you can achieve the maximum possible capacity for a given SNR and a given bandwidth. Okay, so these as you saw in the video, use very long codes, and they have variable nodes and constant nodes, and the decoding mechanism is iterative. Okay, so we will go through the decoding mechanism with an example later, but let's go first through the general characteristics of these Ldpc codes. So this Ldpc code, they are often defined by the parity check matrix H. So the parity check matrix of an Ldpc code is a special matrix as compared to other forms of Hamming codes. So most entries here are zeros, and only there are few ones. So thus the name low density parity check code. And each bit of an Ldpc code word corresponds to a row of the parity check matrix. Okay, and such a code is said to be regular if every row of H has the same number of ones, and every column of H also has the same number of ones. So this is an example of a regular Ldpc code. This is a 10-5 Ldpc code, so therefore it has 5 rows and 10 columns. Okay, and if you see, each row has 4 ones. Okay, each row, if you count the number of ones, it's 4, and each column has 2 ones. So this is an example of a regular LDPC code. Okay, and the H matrix, okay, that you have for LDPC codes, they can be nicely represented by these type of graphs. So these are bipartite graphs, which are sometimes called Tanner graphs. So basically, uh, the 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 rows, okay, so let's take this example of H matrix. So here we have 1 2 3 4 5. So there are 5 rows, okay, so therefore we have 5 check nodes here, okay, and how many columns? 1 2 3 4 5 6. So these represent the variable nodes. So we have 6 variable nodes, okay. So now, if you see this first, let's say the first element of this H matrix, okay, or rather, if you see the first row, okay, so this first row has a 1 in the second place and the fourth place, okay. So these variable nodes corresponds to the I mean the columns, okay. So if you look here, okay, or rather, sorry, the first column, if you look into the first column here, so that is connected to this, I mean that has a 1 in the second row and the fourth row. So this will be connected to the second check node and the fourth check node, okay. So these connections are corresponding to the number of ones in that particular column, okay. Now if you look into this column, which is corresponding to this variable node, so you will see that you have the first 3 ones, so it is connected to the first one, the first check node, the second check node, and the third check node, and there is no connections to the others. Similarly, if you look into the third column, then you will have a connection to the third check node and the fifth. So that's how this connectivity is created, and whatever information we have in this parity check matrix, that can be represented by this type of graph, which is called a Tanner graph, and the number of rows in the parity check matrix will give you the number of check nodes, and the number of columns will give you the number of variable nodes, okay. So now I will show you an example how to use this bipartite graph or Tanner graphs to decode a particular received code word, okay. So let's say we have a Tanner graph like this, okay, and let's imagine that this is your received code word, okay. This is your received code word. So and there is an error in this code word. So whatever we are receiving, so that's that C that we are sending, okay, which is U times G, okay. The let's take the concept of the general block code. So this C, when you are sending it through the channel, so let's say this is your channel and you have the received code word here. So if there is no noise or no errors in the channel, then this R will be equal to C, but usually there is noise, so R is not equal to C. So let's say this is your received code word R, and we are trying to find out the errors in R and decode it so that we find the original code word C. Okay, so let's write the R like this. Okay, so these are the different bits of R. Let's put it across the variable nodes of the Tanner graph. Okay, so now if you look into the check nodes here and find out the modulo 2 sum of whatever is incident on these check nodes. So let's say if you consider this check node, then this check node is receiving an input from this variable node, which is, let's say, 0 now. Okay, so you will have a 0 that is incident here, and this check node also receives a 1 from this variable node. Okay, so if you do the modulo 2 addition of these two, you will get a 1 here. Okay, similarly if you look into this check node, you see that there is a 1 incident from this variable node, there is a 0 incident from this variable node, and let's say there is a 1 incident from this variable node. So these three, if you do modulo 2 addition, 1 plus 0 plus 1 will give you 0. So if you perform the same for all the check nodes, you will see that you have 1 0 1 1 0. Okay, so ideally if this received code word was equal to C, if your R was equal to C, or in other words whatever is here on this line is a valid code word, then all this would have been 0. Okay, okay, so this is intuitive. This basically comes from the fact that C times H transpose is 0. This is true for all linear block codes. Okay, so for the Ldpc code in the Tanner graph, if this was a valid code word, this entire thing, this was a valid code word, then this would have been 0. But since there are errors, this is not a valid code word, so R is not equal to C. Because of those errors, you have 1 0 1 1 0. Okay, so these ones, they are not supposed to be here, so these are called unsatisfied check nodes. Okay, so if you have this situation, then how to decode this linear block code? Okay, so let's look into this. So the first step of the decoding process will be to examine the number of unsatisfied check neighbors for each bit. Okay, so these are the bits in the received code word. Okay, so for each of these bits, so let's look for this one. How many check neighbors it has? So it has two check neighbors, this one and this one, because this is connected to only these two. Okay, and out of this it has one unsatisfied check neighbors. Okay, because this has to be 0, so this is unsatisfied. So let me write the unsatisfied check neighbors in parentheses. So this has one unsatisfied check. Now let's look into this bit. This has 3 check neighbors. Okay, and 2 are unsatisfied. Okay, so you have 2 here. For this one, you have 2 check neighbors and 1 is unsatisfied. For this one, you have 3 check neighbors and 1 is unsatisfied. For this one, you have 2 check neighbors and 1 is unsatisfied. And then for this one, if you get this correctly by now, then this one has 1 unsatisfied check neighbors. Okay, So examine the number of unsatisfied check neighbors for each bit, which we have done. Now the second bit from the left, so this one is the second bit from the left, is the only bit that has two unsatisfied check neighbors. So you look for the bit which has the most number of unsatisfied check neighbors. Okay. So now you flip the second bit from the left. So the idea is to flip the bit which has the most number of unsatisfied check neighbors. Okay. So flip the bit which has most number of unsatisfied check neighbors. Okay. So if you flip the second bit, then the second bit will be 1. Okay, it was 0, so flipping means it will be 1. Okay, and if you flip the second bit, then all these modulo 2 addition will also change. So now we will have a fresh set of check bits here. Okay, and then we will repeat the process. Okay, so we will now, so this is the end of the first step. Now in the second step we will do the same. We will examine the number of unsatisfied check neighbors for each bit. So let me erase the pen here. So in this case, now let's do the step again. So the number of unsatisfied check, so the leftmost bit now after the first step will have the most number of unsatisfied check neighbors. So this particular bit will have the most number of unsatisfied check. Okay, and now you flip the leftmost bit. Okay, so if you flip the leftmost bit, it was 1, it will become 0, and then what happens to the check bit? So now it has been all zeros. Okay, so this actually concludes the decoding process. So the decoding process ends when you have all zeros in the check bits. Okay, so this basically now whatever you have left with, this is a valid code word. Okay, so sorry, so this 0 1 0 1 1 0, this is a valid code word now. Okay, so this is how you decode the LDPC codes. I'll stop here for this particular video lecture, and we will continue the remainder of the error correction codes in the next video lecture. So thank you.